Hello and welcome back to Math 3322. I'm Dr. Heath and today we're going to cover Chapter 8, Section 3. So Section 8.3 is all about functions. Students will be able to understand and explain the concept of a function, including domain and range, different representations of functions, and then we are actually, your textbook covers this third point. However, we are not going to cover this last bit in our course right now. So we are just going to get the basics of functions. All right, so functions, we can think of functions as a rule whereby we're given one value, the function or rule specifies some resulting value. So in these tables, we have a rule. So say, for example, the student gives a teacher a value and the teacher spits out another value or gives us a value back. So in the first case, we have the student says 1, the teacher says 3. The student says 0, the teacher says 0. The student says 4, the teacher says 12. The student says 10, the teacher says 30. So we're looking for a pattern here to find the rule that the teacher is following to give the response. So I first think, okay, well, 1 plus 2 is 3, but 0 plus 2 is not 0, so it's not adding 2 as the rule. And then I think, okay, well, 1 times 3 is 3, 0 times 3, that's 3, 4 times 3, that's 12, 10 times 3, yeah, that's 30. So the teacher's rule in this case could be multiplying by 3. And that would give us the rule, multiply given number by 3. So 3 times n. Sorry, my video is behind there, but it does say 3n. All right, and then in the second rule, we have student says 2, teacher says 5, student says 3, teacher says 7, 5, 11, 10, 21. So again, I start to think, okay, well, 2 plus 3 is 5. Okay, 3 plus 4 is 7, so maybe are we adding by 1 more every time? 5 plus 5, though, would be 11, so that doesn't quite work. So we're not adding by 1 more every time. 2 doesn't really multiply nicely to get 5, but let's see, 2 times 2 is 4, plus 1 gives me 5. 3 times 3 is 9, that doesn't work, but what about 3? 3 times 2 is 6, and 6 plus 1 is 7. So what if I were to multiply by 2 and then add 1 every time? 5 times 2 is 10, plus 1 gives me 11, great. 10 times 2 is 20, plus 1, great, gives me 21. So that rule is going to give us multiply by 2, then add 1. So if we have n, we would get n times 2, so 2n plus 1 gives us our rule. And then lastly, we have this example. So student says 2, teacher says 0. Student says 4, teacher says 0. Student says 7, teacher says 1. Student says 21, student says 1. So in this case, I think, okay, well, maybe the teacher will only ever answer 0 and 1. But what's similar about the times that the teacher says 0 and the times that the teacher says 1? So here, one possible pattern we might see is that if the number is even, the answer is 0. If the number is odd, then the answer is 1. Now, excuse me, this is not the only possible answer. Another answer could be 0 if the number is not divisible by 7, 1 if the number is divisible by 7. So there are lots of different possibilities in what this rule might be, but one is to split it by even and odd. All right, so we can think of a function as kind of a machine. So we have an input to the machine, and then the machine is working according to the rule of the function, and it spits out an output. So if in this picture we have an input of 6, and the function rule is to square the input, then it would square 6 when we put 6 in, and it would put out 36, or 6 squared. So for the function named f, we have what's happening in this example is 4 is being input to our function. The function rule is to add 3. So we use this notation, function notation. We would read this f of 4 equals 7. So the function when the input is 4 is 7 because we're adding 3. So we might ask, all right, what will happen if we input the numbers 0, 1, 3, 4, and 6? So if we input 0, then f of 0 is going to be 0 plus 3, or just 3. If we input 1, we're going to add 1 to 3 to 1, and we get 4. If our input is 3, we add 3 to 3, we get 6. If our input is 4, we add 3 and we get 7. And if we input 6, we add 3 and our result will be 9. So we can write an equation to depict the rule in the previous, like we did in the previous example. So for that example, if the input is x, the output is x plus 3. So f of some input x will output x plus 3. So when we input 0, we output 0 plus 3. Input 1, we output 1 plus 3, etc. So we need to define a function and a couple of other words that go along with function. So a function goes from set A to set B, and it's a correspondence from A to B in which each element of A is paired with, and here's the kicker, the important part, it's paired with one and only one element of B. Okay, so every input yields exactly one output, not more than one, not 0, exactly one output is given to each input. So if we look at an example, if we have a function, potential function, that's rule is for any natural number x, the machine outputs a number that's less than x. So we have to figure out, is this a function or not? In other words, does every input yield exactly one output? In this case, we have that this is not a function because if we say put in the number 10 to our function or non-function, we could yield an output of 9 because 9 is less than 10, but we could also have 10 input and the machine output 3 because 3 is less than 10. So that's not a function. We also have a problem that's not noted here because if we input 1 into this function, there are no natural numbers that can output less than 1 because 1 is the smallest natural number. So 1 would not have any, where other natural numbers would possibly have more than one output. So this is not a function because the input may give different outputs. Okay, let's take a look at this example where we have a bicycle manufacturer incurring a daily fixed cost of $1,400 for overhead expenses and a cost of $500 per bike manufactured. So the cost C of x is our function of the cost daily for this bike manufacturer for manufacturing 8 bikes per day. So we know that the cost of producing X bikes in a day is going to be $500 per bike, so 500x, plus $1,400 as overhead costs. So baseline just to operate their manufacturing expenses, overhead, we have $1,400. So we can write our function as c of x is 500x plus 1,400. Now, if the manufacturer sells each bike for $700 and the profit or loss, if they don't make money in producing and selling x bikes is p of x, then we can write p of x as a function in terms of x. So p of x, they're going to make $700 per bike. So a positive $700 times the number of bikes, x. And then we have to subtract the cost that it's going to cost the manufacturer to make those bikes. So we know it's $500 per bike plus $1,400 in overhead to produce X bikes. And then we can simplify this function to say, all right, it's going to be 700x minus 500x minus $1,400. So 200x is the profit for each bike, but then we have to subtract the $1,400 of overhead here. And then this is just written out for you. So if we want to know the break-even point or the number of bikes that the manufacturer has to produce and sell to break even, given those overhead costs, then what we are going to need to do is find the number of bikes x so that that profit function equals 0. So the profit function, again, was p of x equals $200 for every bike minus the $1,400. So we need to find when p of x equals 0. So that means I'm going to solve for x when the profit is 0. So to solve for this, I can add 1,400 to both sides. And I have 1,400 equals 200x. If I divide by 200 on both sides, then I'm left with 7 equals x. So this bike manufacturer has to make and sell at least 7 bikes every day to break even. And this is just the work typed out for us. Okay, so another way we can represent functions is with arrow diagrams. So on the left, we have the domain of a function, and on the right, we have the potential range of the function. So on the earlier slide, it said domain is the set of values that we're inputting into the function, and range is the set of values that are given as outputs of the function. So we need to figure out if these diagrams represent functions. So what this is saying is, in this picture, 0 is the input of 0 gives the output of this point, the input of 1 gives the output of this point, the input of 2 gives the output of this point, and the input of 3 gives the output of this point. And our question should be, does every input have exactly one output? And in the case of the function on the left, this is a function because every input has exactly one output. Now, if we look at the function or potential function on the right, we have 0 yielding 1 as the output, 1 yielding 4 as the output, 2 yielding 4 as the output, and that's okay. It's okay if two numbers go to the same output, but what makes this mapping problematic is that 3 gives 2 different outputs. So this is not a function because 3 does not have just exactly one output. Okay, if we look at these functions, we need to find out if it's a function, or excuse me, potential functions. We need to know, is it a function? If it is, then what is the range? So what are the values that are being output? So and when we look at this first example, 1 is going to the output 2 and the output 4. So this should tell us automatically that this is not a function because 1 is giving us more than one output. If we look at this potential function in the middle, we have A mapping to 1, C mapping to 2, but B does not have an output. So this is also not a function because we need exactly one output for every input. And if B is an input in the domain of our function, then it needs to have exactly one output. So this is not a function. And then if we look at this last example, X maps to A, Z maps to B, and Y maps to C. And behind my head, I think there's also a D in this picture. So this is a function, but the range is just A, B, and C, because those are the only values being mapped to. All right, so if we have the set of John, Mike, Joan, and Sue mapping to the colors Brown, or last names Brown, Smith, and Doe, John has the last name Brown, Joan has the last name Brown, Mike has the last name Smith, Sue has the last name Doe. This is a function. Even though John and Joan have the same output, this is a function and the range is Brown, Smith, and Doe. And then here, these inputs all map to one output, so this is a function and the range are all of the values of our outputs, 1, 4, 7, and 10. Okay, another way we can represent functions is using tables and ordered pairs. So in this example, the L&B Lawn Service distributes the following fee schedule to their customers. It gives the price for mowing large lots given the number of acres of the lot. So if your farm or land is 1 acre, then you have to pay $50. If you have 2 acres, you pay $85. 3 acres, you pay $120. 4, $155. For 5 acres, you have to pay $190. We can also represent this function as a set of ordered pairs. So the ordered pair, an ordered pair is just where we have in parentheses one value and another value. And our first value is the input, and our second value can be the output. So here, the ordered pair 150 corresponds to the first table entry here. And then we have 285 as our second ordered pair. Our third ordered pair would be 3, 120. Our fourth ordered pair is 4, 155, and our fifth ordered pair is 5, 195. And so we can write that as a set of ordered pairs. So we can look at sets of ordered pairs to determine if it would represent a function or not. So if it does, then we can also yield the domain and range. So in this case, we have, if I think about this as values, then I have 1, and 1 maps to 2, in my first ordered pair, so I've looked at that one. And then my second ordered pair tells me that 1 maps to 3. Now that immediately creates a problem for me because 1 should only have one output, exactly one output. So this is not a function because 1 has 2 different outputs. If we look at the second possible function, we have 1 mapping to 1/2. Get my red pen. Then we have 2 mapping to 1/3. We have 3 mapping to 1/4. And 4 mapping to 1/5. So this is a function. Every input has exactly one output, and our range in this case is going to be 1/2, 1/3, 1/4, and 1/5. And our domain is all of our inputs, 1, 2, 3, and 4. Okay, if we look at this example, we have inputs of 1, 2, 3, and 4. We have outputs of 0 and 4. 1 maps to 0, 2 maps to 0, 3 maps to 0, and 4 maps to 4. This is a function because every input has exactly one output. It's okay if they have the same output. They just can only have one. Our domain is the set 1, 2, 3, 4, and our range is just 0 and 4. Okay, and then this one is a little more abstract. So our set of ordered pairs is all of the pairs A and B, where A is in N, the set of natural numbers, and B is 2 times A. So this is going to be a function because we can always take every natural number and multiply it by 2, and we'll get exactly one answer. And the domain will be all of the natural numbers, but the range will just be all of the even numbers because we can only ever get outputs that are even in this case. We can also, if we have a domain and range that are numerical, we can represent functions as graphs. So graphs are a very common way of representing functions. So this is back to that lawn service example. We can see how if you have 1 acre of land, you would have to pay $50 to have your lawn taken care of. 2 acres is $85, 3 acres is $120, 4 acres is $155, and 5 acres is $190. And we can actually see that this is going to end up making a line, a linear function here. So last example here, if we think about this graph, we want to think about why a telephone company would not set its rates for calls as depicted on this graph. So if we look closely at this graph, it is not a function, and it's not a function because, say for example, if you make a 2-minute phone call, then the company could charge you either 50 cents or 85 cents. And same for a 1-minute call, they could either charge you 50 cents or 85 cents. So this is not a function because not every input has a unique output. And so for our telephone company, they want their prices to be clear which charge you're going to get. So every possible number of minutes needs to have exactly one cost associated with it.